start with DC power supply. DC power supply is sorry. Okay, so let's start with power supply. So basically, power supply is nothing but the combination of rectifiers and filters and regulators. So what happened that the AC cycle consists of negative and positive half cycle. Then bridge rectifier convert that negative and positive half cycle into a pulsating DC. Then a filter convert that pulsating DC into the approx pure AC, you can say. And after that, we get a approx pure AC. Now the regulator will regulate the voltage and give the constant voltage to the power supply. Sorry, to the output of the power supply. For this we need transformer, diode, rectifiers, and filters and regulators. Okay. So for this, you need to know the basics about power supply. What is power supply and how does it affect the whole system? Because without power supply, the system will not work. A system need a constant power supply to work at a operating voltage and etc. Now, this is the circuit of the rectifier. It is a bridge rectifier, so it doesn't need any type of transformer here. Okay, and this is the output. Now what we have to do? Add four diode blocks. Add four diode blocks from a Synscape foundation library. All right. Okay. Next, connect the diode block in the orientation indicated by the circuit diagram. Okay. So I have to connect this diode to this. Then we have to connect two positive faces, sorry, two negative faces and two positive faces. Add an AC voltage supply. AC voltage source. The positive part is connected to this side, and the negative part is connected to this side. Okay. Let's make it like real rectifier. So I will. Okay, that is good. Then connect the reference ground. Okay, and obviously we have to add the solver configuration. Okay, in the AC block, I have to set the P to add a resistor from the foundation library of PO. Resistor from the foundation library, set the value to 50 ohms. Adding the value where I have to add it, connect it to the bridge rectifier label as a V out. diode minus resistor plus. Resistor plus and time has to be set around 2 by 60 by add capacitor from set of foundation library, and I have to add a resistor parallel to resistor. Set the value of capacitor to 800 microfarad. 800 microfarad. Next, the future session. Now, add an ideal transformer. Transformer block from the foundation library. Where is the foundation library? Transformer. Ideal transformer. The ideal transformer library to set model 2 winding ratio 24. Winding ratio should be 24. Next, we have to add here, add an electrical reference block to the model connected to the negative output of the bridge rectifier. Okay, okay. Connected to the negative output of an bridge rectifier. Wait a minute. First of all, to make the circuit more understandable. Change the winding ratio parameter. Okay. The next task. What we have to do here? Add a new resistor from the foundation library. Resistor from the foundation library, set the value to 33 ohms. 33 ohms. Then what I have to do? Create a Zener diodes as follow. Add a diode from the foundation library. Sorry, not foundation library. From electrical semiconductors library. Check the model Zener diode box enable. Here I have to set model Zener diode blocks enable, and in the breakdown section I have to set value to 3 volt. Reverse bias has to be 3 volt. Okay. Next. Now we have to connect it like this. First of all, we need this. Sorry, we have to make it at across. Alright, so what we have to do, we have to write like this. Then I need a diode. Plus the diode. Sorry, it is not connected. Not disconnected successfully. Next, future section. So basically, what is Zener diode? Zener diode is a special type of diode which does not allow the voltage to increase after a limit in a reverse bias. It is like a regulator. Sorry. Now, navigate to the temporal trigger section of a block parameter dialog box. Fault block. Navigate to the temporal trigger section of the block parameters dialog box. Temporal trigger section of the block parameter dialog box. Choose on yes. Set this simulation time to 0.05 second. Okay. Now, what I have to do? Connect the fault block parallel with the capacitor. I have to connect this block parallel with the capacitor. Plus and plus, and minus and minus. Okay. Like this. It is set to that video. 0.05 second. Okay. Now add a fuse. Fuse connected between the ideal transformer and the diode. Between the ideal transformer and diode. Set the rated current to 5 ampere. 5 ampere. Okay. Next, let's go to the next session.
An op amp, or operational amplifier, is a powered amplifier. Op-amps are the basis for many circuits, like audio amplifiers, waveform generators, and filters. These circuits are made up of individual op-amps that amplify basic computations, like sums and differences, or integration and differentiation.
Yes.
Before we learn how to include
Op-amp can
op-amps in
also
your
perform.
SimScape models, let's
Sorry.
review.
Often, sorry. Op-amp can also perform the uh, arithmetic, or you can say mathematics, like logarithmic and anti-logarithmic, and because of that we can also do the mathematics like multiplication and division. But because the op-amp gives the gain at the output, we have to set the value of the resistor R1 and RF to make the gain minimum, so the output will be not saturated. Okay, so we will learn about that later.
Review some basic properties of op-amps. Op-amp chips can have many different architectures, but are represented using this symbol in a circuit diagram. The terminals on the left are the input terminals. The input voltage is the difference between the positive and negative terminals. On the right is the output, the amplified signal. In practice, op-amps are most commonly used in a negative feedback circuit.
Yes.
That is, a portion of the output is fed back to the negative terminal. This feedback stabilizes the op-amp's behavior. Okay, sounds good. So, how do we know what the output voltage is? Well, this particular circuit has an easily derivable input-output relationship.
Yes. But because it is non-inverting amplifier, that's why.
But what about this circuit?
Okay, so basically this type of circuit is integrator with low pass filter.
Well, we could go through Kirchhoff's laws for every node and loop, but that might take a while, and it'd be pretty easy to make a mistake. Instead, let's see how we can simulate it using SimScape. Let's go back to our non-inverting amplifier as an example. To start, we'll insert an op-amp from the SimScape Foundation library. This block represents an ideal op-amp.
Yes.
As you may recall, the ideal op-amp is a standard set of assumptions used to describe most op-amp behavior. However, if you do need to capture non-ideal behaviors, such as finite gain or limited bandwidth, the SimScape electrical library has other op-amp implementations. In this course, we will always assume ideal behavior. Now that you have the correct block, building the op-amp circuit is the same as building any other SimScape model. Add blocks, assemble them according to your circuit diagram, set parameters, and simulate. And indeed, the output is what we expect. Building more and larger op-amp circuits is as easy as adding and swapping fundamental components. Ready to see for yourself?
Yes. Let's start. Add a AC voltage source. Add a AC voltage source and add a op-amp. Operational amplifier. Now, AC voltage. The peak will be 1 millivolt. Okay, 1 millivolt. And add an operational amplifier to the model. You can flip that vertically. Connect the negative part of an AC source to the part of the AC voltage source and the positive input to the op-amp. Connect the negative port of the AC voltage source and the positive input port of an op-amp to an electrical reference. Okay. Okay, so how can I rotate this? For that I have to go to the step 1. and flip down. That is perfect. Connect the positive portion of back to the reference. Now add a resistor connected resistor and set the value to the 10 ohms. 10 ohms. Add a second resistor and set the value to again 10 kilo ohms. Okay, 10 kilo ohms. Next, add a third resistor. Add a third resistor model. Connect the positive port to the okay. Let's see. It's acting like a feedback, so I have to add electrical reference. There is no, so I have to use a new resistor, I guess, because the value is must connect with the solver configuration work. There is no solver. Okay, so there is no solver configuration that I have connected. Let's connect it. Next session. Now copy paste the existing resistor blocks, such as there are two there are two 1k kilo ohms, there are two 1 kilo ohms and 200 kilo ohms. Next, okay, add a DC voltage source and set it to DC voltage source and set it to 5 millivolt. Okay, 5 millivolt. Does the model contain the following DC block? Two DC blocks. Yes. set to 1 DC volt. I think I have to connect it, otherwise it will give me the same problem. So let's connect. Sorry. Set to constant. It shows from foundation library. The value is set to 5 millivolt. Okay, now it is perfect. Complete the connection to match the circuit diagram. You can add an additional electrical reference. No, I don't need that. Oscillating circuit. Now we are reached to the oscillating circuit. We have to design the oscillators. So I think I have completed the non-linear part and the op-amp part. Then there will be filter and project. So I will complete up to filter, and for project we will go and see it for next video. Okay, so add a band limit operational amplifier. Okay, so why it is not working? Band limited operational amplifier from skip electrical integrators. Then I have to set the parameters, that is set the minimum output, that is VMIN, which is V mean has to be minus 10 volt, and maximum has to be 10 volts. Okay, set the output resistance. This is output resistance, this is output resistance to 0.1 ohms, 1 ohms, and the input resistance is perfectly set. No, and the maximum slew rate, this is maximum slew rate set to be 1e6. Okay, submit. Next. Now add a resistor capacitor block to your model. Foundation library, capacitor from foundation library. Set the resistance to 100 ohms. 100 ohms, and capacitor to 10 microfarad. 10 microfarad. Add two more resistor block to the model and set the value for both with this. Set the value for both E3 means 10 kilo ohms. Next, the different types. Now, make the connection from the circuit diagram shown in the diagram. Sorry, make the connection in the circuit shown in the diagram. So first of all, we need amplifier, which is this. Then we will need 10 kilo ohms. Okay, so we are making a proper. Okay, so this is nothing but a symmetric trigger. We are making a proper symmetric trigger here. But why we are using capacitor, I don't know. Let's see about that. No, this is not a symmetric trigger because there are two feedback here. I don't know what we are making. Let's see about that later. After the following, connect the bandwidth minus to the capacitor minus. Okay, I have to just reverse it. Okay, so I understand what's the main problem here, that I have connected it to non-inverting terminal. Inverting, non-inverting. That is perfectly perfect. Next, set the expand capacitor. Select and expand the capacitor voltage. Capacitor voltage is set. Capacitor voltage option and set the value to 1 millivolt. 1 millivolt. Okay. And the priority is already set to high. Yep. It's set to 1 millivolt. Set the value to 1. So I have set the value to 1 millivolt. That is giving the problem here. The capacitor value is already set to 1 millivolt. Does the following block value matches the capacitor volt? Yes, it is perfectly. Oof, 10. give me the same problem. Why? Hmm. Okay, we will go to the next part. I think this is a network problem.
Electrical filters are everywhere. You might have encountered filters if you've chosen a radio station or used a pair of noise-canceling headphones. In this video, we'll review how filters relate to electric circuits and how to simulate and analyze filters in Simscape. Imagine you had a measurement of the vibrations in a building. Your vibration recorder converts each shake to a voltage. In your vibration signal, you will see many frequencies. The steady hum of machinery in the basement, rumblings from trucks driving over a speed bump, and a constant 50 or 60 hertz from your lighting. But what you really care about is an experiment you're running that produces a high-frequency signal. So, before you can analyze your data, you need to filter out all those lower-frequency vibrations. You can do this using a high-pass filter. As the name suggests, a high-pass filter allows only high frequencies to pass through. An RC circuit can act as a high-pass filter. The voltage across the resistor will be maximal at high input frequencies. It has a cutoff frequency of 1 over RC. Below this frequency, the output amplitude will be smaller than the input. Above this frequency, it will be nearly equal to the input. If you choose your resistor and capacitor such that the cutoff frequency is higher than that of your basement machinery, trucks, or lighting, you can make their contribution to the signal minimal, making the measurement you want more obvious. So far, we've thought about filters by considering the amplitude of the signal over time. But since filters are used to process a signal based on frequency content, it's more useful to think about filters in the frequency domain. To see if our filter is working, we want a measurement that shows us how much of each frequency is present in a given signal. By looking at a frequency spectrum of the input and the output, you can see if your signal is being attenuated at a particular frequency. In an electrical engineering lab, you can make such a measurement using a spectrum analyzer. And in Simscape, you can do the same in simulation. The spectrum analyzer block can be found in the Simscape Utilities library. This block expects a discrete Simulink signal. Therefore, to obtain a frequency spectrum for a Simscape value, you will need a sensor, a physical signal to simulate converter block, and a rate transition block. The rate transition block discretizes the signal by sampling at a rate specified by the sample time. When choosing the sample time, you want to prevent aliasing. Aliasing occurs when a signal is sampled in a way that makes it indistinguishable from another signal, like how a video of a wheel can make it look like it's moving backward. Avoid aliasing by choosing a sampling frequency twice that of the highest expected frequency in your signal. For a continuous time signal with a maximum frequency of b hertz, that means your samples should be at most 1 over 2b seconds apart. Let's come back to an RC circuit and see how to choose a sample time and what spectrum analyzer can show us. This circuit has input frequencies of 10, 50, and 400 hertz, and a cutoff frequency of 318 hertz. We'll connect a voltage sensor, physical signal to Simulink converter block, a rate transition block, and the spectrum analyzer. Our sample time should be no larger than 1 over 800 seconds. We'll round that to 1,000th of a second. We can also measure the input signal for comparison. By simulating the model, we can see that the output below the cutoff frequency is reduced, as we expect for a high-pass filter. Now it's time for you to practice with Spectrum Analyzer. Click Next below to try it yourself.
Let's try. Okay. So how much was this completed? I have to watch that because add a resistor and capacitor from the foundation library. Resistor, capacitor, On the foundation library, set the resistance to 100 ohms. 100 ohms and capacitor to 50 microfarad. 50 microfarad. Next, add a programmable voltage source. From which library? Electrical source library. And set the AC peak magnitude to 1 volt. Next, open the block parameter dialog. Why my internet speed is not good? Although I have 10, 500 Mbps plan. Okay. So dialog box. What I have to do? Open the dialog box for the programmable voltage source and native to the frequency section. Sorry, native to the navigate to the frequency section. Set the following parameter to produce a strip of between 1 and AC frequency set to ramp. AC voltage frequency set to 1 Hz. Rate of change is set to 8 Hz. Start time set to 0 and stop time set to 10. Connect the programmable voltage source, resistor and capacitor in the series. Okay. First resistor, then capacitor, and then this. Add a voltage sensor, foundation library, and the PS. And I think I need a scope also. Scope. Set scope here. I will set the converter here, and the voltage will set here. Now, connect them so that the voltage across the capacitor will be displayed. This is the frequency we are getting. So now I have completed, I think, 50% or 40%. Split the programmable voltage AC source. Add two AC voltage source. I have to modify it. Modify one of the ACs to having the peak amplitude of 1 and frequency of 20 hertz. Other has to be 0.2 volt, frequency of 200 hertz. Connect them in series like this, I guess. Alright. Set the model's stop time to 0.2, 0. To see the dynamic clearly. Clearly. Add the second voltage sensor. We need to sense the voltage across AC voltage source. So setting setting will be open. In that we have to go to display, show legends, number of ports should be 2, enter, and that's all we need. Cancel. We're gonna patch here. Let's give it the name like v out is submit. So let's see the result is good. Add a 4 AC voltage source block from the foundation library. AC voltage source 60 hertz, 60 hertz. Okay, I will set like 150, 350, 450. Connect all the components to the model series RC. Let's see the solution here. So it has to be in series. Then there is the RC circuit. We need a ground known as a reference. Add the voltage sensor, PS converter, and scope. Capacitor. Add the rate transition block from the Simulink signal attributes. Instead of scope, we have to add it here. In that we have to parameters. Set the output port sample time to 1 by 1000. Spectrum analyzer. Kinscape utilities connected to the port. Set the stop time to 4. Hmm. Now what I have to do? Add an inductor and capacitor from 35 millihenry. So I have set it the value, and now the value of capacitor will be 10.6 microfarad. Am I right? Yes. New filter circuit is shown below. That's that inductor. Perfectly. Why? Yes, it is connected perfectly like that. Then why it is giving the problem? Does the following block value match the plotted value? Yes, but it is giving the error na. 10.6 microfarad. Okay, that is perfect. Next, add the voltage sensor. Voltage sensor, PS, and spectral analyzer ray transition and spectral analyzation for simulating with these. Let's see how much course is completed. Okay, so we are on the project part, so I will not complete the project part. Instead of that, I will go to the amplifiers, that is op amp. Okay,
Electrical filters are
okay, so I will do this part later. For today I think इतना काफी था. Okay,